Oh my God.
Welcome back, everybody.
Thank you.
Let's start with this, a review. I see some, just based on yesterday's discussion, I forget when. Let's review some of this, and then we'll continue to the next chapter. So let's please try to put everything we know about capacitors. Okay? Capacitors, they're made of what? What do you need to make a capacitor? Two conductors. Okay, good. What do capacitors do? They charge. Charge. Okay, good. Perfect. So here's a capacitance. And C, what's the definition? Q over V. Good. Q over V. All right. So let's just try to make sure that we understand what's going on. Capacitance is Q over V. By the way, the units are farads, right? 1 farad. It's a coulomb per volt. Coulomb per volt. So is C equal to Q over V specific for any capacitor, or it's general? General. That's the definition of capacitance. Okay, that's the definition of capacitance. So now, specifically for parallel phase capacitors, parallel phase capacitors, they look like this, right? The distance between the two plates is D, and they extend this way. The area is A. What was the capacitance for this one? Good. Epsilon naught A over D. You should know this at all times. You should not think about it for this one. So this is specific for parallel plates. This is just the general definition of capacitance. It's always a geometric quantity at the end. All right, good. Next thing, how do we charge a capacitor? You use a battery, right? You use something that will remove charge from one plate and places it on the other. Okay. So let's say this plate here is positive Q, and this plate is minus Q. Okay? What's the total charge of this capacitor? So yeah, good. That's why I asked that question. When we say Q over V, we don't mean, obviously, you will always get zero, right? The total charge is always zero. What we mean by the charge on the capacitor is the charge on one of the plates, the absolute value. So usually the positive plates, right? So when we say the capacitor has charge Q, we're thinking about just one plate. It was charged to Q. Next, how much energy is stored in a capacitor when you charge it? Okay, let's write it down. Energy. The symbol is U, right? What was it? 1/2 CV squared. There was another form, which was 1/2 what? QV. And another one? Q squared over 2C. Yeah. What are the units of this thing? Of this U? Joule. Then we discussed energy density. Little u. It was capital U over volume, right? So this one is joules per cubic meter, right? Joules per cubic meter. Okay. It was related to the electric field. It was 1/2 epsilon naught times the electric field squared. So that was the energy density in the field. Okay. Next thing was we connected capacitors in series and parallel, right? We connected capacitors in series and parallel. So I would like to also discuss that. And I'm going to write it on this one. This one here. So here is a capacitor. Let's say this one here is negative Q. Here is positive Q. And the distance is D, right? All right. When you have two infinite sheets of charge, what's the potential at this one? Okay, good. And then the potential here, remember the electric field is this way, right? It was ED, right? And it's just V, right? V. So when we say the potential difference is, let's say, 10 volts, it means this one has 10 volts higher than this. Right? The positive plate is at 10 volts higher than the negative plate, so if it's 10 volts. Is that clear? All right. So why am I saying this? Because, so now let's make the capacitor a little smaller. Here is the capacitor. Here is minus. Here is plus. If I start here and I end here, here's my initial, here is my final. What's the voltage? Is it a positive change or a negative change? We go from minus to plus.
Positive.
Positive, yes. Because you started at the lower potential and you ended at the higher potential, so the change in voltage is just positive V, right? But if you go from plus to minus, the change is negative. Is that clear? Okay. So please keep that in mind. All right. So now, let me go to connecting capacitors in series and parallel. Series, they look like this. Let's write the word series first. You got a capacitor followed by another one, right? Followed by another one, followed by another one, and so on. And they're equivalent to one capacitance here called C equivalent. Here is C1, C2, C3. So in series, all the capacitors, they have the same potential or the same charge. Charge. So in series, Q1 is equal to Q2 is equal to Q3, and they are equal to Q equivalent, right? The charge of the equivalent capacitance. Capacitance, to find it, you have to do the equivalent, you have to do add the reciprocals, right? And then do the reciprocal of that. If you have just 3, you stop. If you have more, so that's that. The next one is parallel. Was when you have the following situation, you have a capacitor here, followed by a capacitor here, followed by another capacitor here, possibly, and it can go on. So C1, C2, and C3, and if we were to replace all of these by just one, called C equivalent, okay, what would C equivalent be? Actually, what was special about these? What's the same for all of them? The voltage, good. So V1 is the same as V2, it's the same as V3, and it's the same as V equivalent, good. And C equivalent, how do we find it? Just add, just simple addition. 1, 2, 3, no reciprocal or anything, just add. Okay, sounds good. Okay. This brings me to the next step. Yesterday I saw some confusion about what's in series and what's in parallel, and why is this considered series and why is this considered parallel. So let's clarify that. Let's do it. Pull this next board. So here is a battery. Here is a capacitor. Let's call it C1. And here is another one, C2. And here is C3. And here is C4. And let's say we just have that. So let's just get some terminology. A point where two or more wires meet is called a junction. This is a junction. This point here, you got junction. This is another junction. Okay. Is this a junction? No.
No.
Think of pipes and water flowing. If water flows, when it gets here, it has two paths. Some water goes this way, some goes this way. But here, it's just a corner. All of it goes this way. And then there is another term that I would like to also mention. So these are junctions. And then the other term is the term branches. A branch. What's a branch? Here's a branch. Here's a branch. Here's another branch. Branch is just basically on the same line. That's called a branch. How many branches do we have here?
One.
We have three. We have three branches. This one, the middle one, and then the left branch. Three branches. Now, capacitors are in series if they are on the same branch. Same branch, they will be in series. For example, is C2 and C4 in series?
No.
No. Are they on the same branch?
No.
No, they are on different branches. C4 is on this branch. C2 is on this one. How about C1 and C2?
Yeah.
They are. They are on the same branch. So, yeah, so definitely C2 and C4 are not in series. How about C4 and C3? What kind of connection are they in?
Parallel.
They're in parallel. Good. How do we know that they're in parallel? Now, another thing is about wires. Could we have drawn the wire like this? Would it? I will ask you. I'm going to redraw it and tell me if it changes the circle. No. Okay. Wires can, they can bend and so on. It doesn't change anything. Okay, good. All right, good. Next thing. So don't, we usually draw them straight because they just look nicer and less confusing. Who wants to do this, right? Why would you do it? But they could be drawn like that. On the other hand, let me ask you this. What if, let me erase C4 from here and put it here. Anything changes?
No.
No. Yeah. It's still on this branch. Good. So usually, to make it clear, we usually draw it here. Now it's probably obvious that C4 and C3 are in parallel. They're in parallel. So, which brings me to this loop rule that you can double check if something is parallel. It should be obvious after you have done enough of these. It should be obvious if two things are parallel or series. But let's start here. Which one is the positive end of the battery? Yeah, this one. And this is minus. So charges will go here. So you have this one being plus, right? This would be minus. This would be plus. This would be minus, and this would be plus. This would be minus. This would be minus. This would be plus. Now, C3 and C4, I'm saying they're in parallel. If they're in parallel, what do they need to have? The same voltage. Good. So let's do this loop rule thing. Loop rule says if you do a closed loop, the potential when you come back to the same point has to be, the potential change has to be zero. Okay. So here is a loop that has nothing to do with anything. Here And if I come back, the change in potential is 0. Is this a useful loop though? No, it has nothing to do with the circuit. It's still true, but not relevant. So a relevant loop would be a loop that's on the circuit. So let's choose something that's here. I want to prove or show, convince ourselves that the voltage across C3 is the same as that across C4. So let's start anywhere we like. I like to start at the negative plate and then make my circuit. You will see why in a second I like to start at the negative plate. There's nothing, you can start anywhere you like, but there is a nice thing here. So I'm going to go around the loop and come back to this point. The loop will involve C3 and C4 because I'm concerned with that. So let's start here. When we cross C3, what's the change in potential? Positive, and let's name it. What can we name it? V7 or V3? V3, that's a better name, right? So let's start here. So I got V3. Is there any potential change here? No, because it's equipotential, right? It's a wire. Conductor. So now I get here, I cross this capacitor. I'm going to go from here to here. There will be a change in potential. Is the change positive or negative?
Negative.
Negative because you went from the higher to the lower, from the plus to the minus, so a minus. And then what's a good name for this potential? V4. Good. Nothing happens here, conductor. And now we come back. So what's the total change? 0. So this tells me that V3 is equal to V4 regardless, always. So these are in parallel. So I hope it's a little more clear, but you have to do problems in order for you to understand. To finish that. Trust me, this is actually easy stuff compared to what we did before, right? To vectors that, or compared to magnetism that would come up. But this is, once you get the hang of it, it's fairly, fairly doable. I think we talked about all this. So now the next topic, which is dielectrics. So I'm going to start erasing there, and then I will come back and erase this. Yeah.
So C1 is positive on the left side of the capacitor and negative on the right.
Yeah.
But then why is it positive for the top of C3 and for the top of C4? Wouldn't it be negative throughout that whole capacitor?
Oh, sure. So think of it. So you got positive charges, they go here, right? And these positives, they attract negatives. Where did the negative charges come from?
The other side.
From this one and this one. Yeah. So if you take away the negatives, these would stay positive. Okay. So I'm going to. Can I erase everything, basically?
Yeah.
We're going to talk about dielectrics, right? And so, what are they and what do they do? Erase also this.
Ada yang begitu seperti itu atau kupluk banget 2 kali 3 lah kadang-kadang ada yang gitu harus bisa.
So dielectrics are insulating materials that get placed between the parallel plate capacitors or between capacitors to either structurally hold them or and also change the capacitance, increasing basically. Because we've been talking about a parallel plate capacitor. After all, there is a plate, there is another one. If I let go, it will just drop on the other. It will just fall, right? Gravity will pull it down. So we need something in between to hold it. And it's usually a dielectric that can be filled. This gap between them, you will put a dielectric. Okay? So that's one purpose it serves. It needs to be insulating, because if it's conducting, it needs to be insulating, I'll tell you why. So here is the here is a capacitor. Here is minus. Here is plus. Okay. And this is plus Q. This is minus Q. And the electric field is this way. Let's call it E0, E naught. The distance is D. And of course the area is A. So the electric, the potential difference between these two plates, what would the potential difference be in terms of E and D? ED, good. E times D, or E naught, right? What do you call it, E naught? The capacitance, C naught, is equal to, and by the way, E naught is equal to sigma over epsilon naught, so it's Q over the area, and then epsilon naught times D, and capacitance would be epsilon naught times the area over D, right? That's what it is with a parallel base capacitor. Anything? This looks okay. So far, it's everything we have done. So now we're going to fill up the space between the two plates with a dielectric material. Yeah.
For C, would Q also be a numerator?
I'm sorry.
For C of 0, would Q also be a numerator? Do you have epsilon naught times A divided by D?
Yeah.
Wouldn't D also be multiplied by Q in this case?
Q should disappear. Needs to disappear because C is Q over V.
So wouldn't Q be a numerator in this case, or
It would be
a numerator?
no in here. It should just disappear. Let's think about it. Here it is. Definition of capacitance is Q over V, right?
Yeah.
Yeah. So I get Q over here is V.
Oh, okay, I understand.
So Q just cancels, right?
Gotcha. Yeah.
Okay. So you get epsilon naught A over V.
Gotcha. Perfect.
So whenever you get capacitance, it should just be a geometric thing. No Q, no V. It should just, at the end, it should just areas and distances. Okay. So what we're going to do is we're going to fill up this thing by a dielectric. So we're going to fill up with a dielectric. And then ask what happens. So it's the same capacitor, but we're going to place between the plates a dielectric. The dielectric will be this material here. I'm going to make it with green. So you got some green material. That's a dielectric. It needs to be insulating, and the reason it has to be insulating is because the charge here is Q. Q, this is minus Q. If it were conducting, positive charges will flow from here to here, or negatives will go from until the two plates will just become neutral. But in an insulating material, are charges free to move? No, they're not. So the charges cannot flow through it. So that's why it needs to be insulated. So having said that, whatever the charge used to be, when you put the dielectric, it will still remain Q. Positive Q here, minus Q there. Okay. It will still be the same charge. So electric field is still from left to right, but the dielectric is still made of atoms, and atoms have pluses and minuses. So even though the charge is not allowed to move across the dielectric, it's allowed to be polarized. So what it does, these positive charges, they will push away on every atom. So let's take one atom. Here's one atom. I'm exaggerating, right? Making it bigger. What happens to the positive charge of that atom? It will be pushed left or right? Left. How about the minus charge? Right. And now think of the next atom. Right? And then think of the whole string of them. And then everywhere also. So now, our electric field due to the two plates is this way. The electric field due to the two plates is this way. Let's call it E naught. Now let's look at these little charges here, little dipoles. This is plus, this is minus, so there will be a little electric field from the plus to the minus. There will be a little electric field here from the plus to the minus. And then think of all of the ones that are, I just drew two, but obviously there are many more. So these, they set their field to the right. Your initial field is to the left. So they will partially cancel, wouldn't they? So the total electric field will be less than this. Will be less than this. So the electric field now, let's call it E prime, will be whatever E naught used to be. It could be half. It could be a third. It could be a 20th. It could be some factor less. It would be reduced by a certain factor. So that factor is called, it would be reduced, it would be divided by this thing here called kappa. Yeah. That's called the dielectric constant. This is the dielectric constant. It doesn't have any units, right? Because electric field equals electric field. It must have the same unit, so this one should be dimensionless.
There's also the idea of like a dielectric constant in organic chemistry. Do they calculate those constants the same way?
I'm not familiar with it from
Okay.
organic chemistry, but I assume if they use the same term, probably the same thing.
Yeah.
Yeah. I haven't taken chemistry in a long time. Sorry. Yeah. So yeah, good question. So what happens? The electric field gets divided. So now here are some dielectrics, some numbers. If it's vacuum, the dielectric constant is just 1. Okay? Nothing happens. Just E naught divided by 1. Okay? If it's air, it's still almost 1. If it's air, it's what? 1.0005 something. Okay? So it's almost 1 also. Yeah.
Wait, so the electric can be an air? Like, can be just air?
Yeah. So air is basically, you have nothing in there, so it's almost 1.
Then why is the capacitor not like attract?
Yeah, they have to be held somehow. They have to
So
be
air,
held somehow.
air can hold.
No. So usually they're held by something, right? So maybe somebody holding from the right and someone holding from the left.
Oh,
Yeah.
okay.
So let's go to how about other dielectrics, right? 1 is not a very interesting number. It's basically a vacuum. Now, if you put silicon in there, it says here it's about 11 or 12. Methanol, the liquid, it's 33. Pure water, it's 80. You put pure water in there in between the plates, it's 80. Just, nobody puts pure water in electronics, but just dielectric constant in water, of water is 80. And so on. There are different materials that have different dielectric constants.
80.
As in, oh, sorry. Yeah, it is. It's a property of the material. Yeah, it is a property of the material. Yeah.
So to be a dielectric,
There
does
is
the thing have to
about
have
what?
like dipole-like properties?
It has to be an insulator. Yeah, it has to be an insulator. It could have a dipole, or it could just be polarized.
Oh,
Like this.
okay.
Yeah. So,
Silicone itu
uh,
silicone karat atau silicone?
and I have a material here that I can't even, a compound that I can't even pronounce, I can't even read
Either
the
silicone
chemical
or
name.
silicone.
Potassium.
Dielectric constant, yeah, something like that. It's about 34,000, okay? Something. So you can have a dielectric constant that's large, okay?
What? What would be the benefit of using the dielectric constant?
Let's,
Oh,
yeah.
Okay.
Yeah. Let's keep going. Yeah, we will get to it. Yeah.
The kappa for silicone, you mean like silicone the rubber or silicone aluminum?
It didn't specify, so I don't know.
Does it ends with an E or F?
Huh?
Ends with
They just wrote the word.
It's probably the element.
Yeah.
It's probably.
Yeah, I think it's the element. It says silicon, so yeah. Yes.
So I'm assuming K is always greater.
Yes.
It should be the
Yeah.
element, not like polarized.
Okay. Let's. So that's electric field. So now let's think about what happens to the potential. So what happens to the electric potential? So let's stay here. So if the electric field gets reduced by a factor of kappa, let's look at V prime. What happens to it? The potential difference now between them decreases by what factor? By kappa, yeah. Because remember, potential difference is ED. So, but now E is no longer E naught, it's E prime times D. And so it's 1 over kappa E naught times D. And that's equal to 1 over kappa V naught, right? V naught is V naught. Now, capacitance. Let's look at what happens to the capacitance, C. We can call it C prime. It will be Q over V prime, right? Because remember, Q, has Q changed on the plates? No. So I get Q over 1 over kappa times V naught. That equals to kappa times Q over V naught. What's Q over V naught?
C now.
Yeah, C naught. Yeah, maybe I should have put. So it would be kappa times C kappa. So what happens to capacitance when you put a dielectric? It increases by a certain factor, right? By some factor. Right? And usually people, they don't put C prime, we call it C kappa. That's the capacitance with the dielectric inserted. Yeah.
I'm not familiar with circuits, but what's the benefit of like increasing capacitance and capacitance?
You can hold more charge for a given voltage.
Well, what's the benefit of holding more charge?
We'll talk about more on capacitors when we discuss
So
it.
you
Yeah.
can use like bigger appliances? You can use bigger appliances?
Maybe. Yeah. So, yeah, definitely you want different capacitors for different reasons. So let's. Oh, I'm here. Let's do a couple of examples here. Couple of examples, and then we'll go on to go on to the next chapter. So please follow with me this example. Here's a battery, and here's a capacitor. So the battery is 160 volts. Okay. So the battery is 160 volts. The capacitor, let's call it C naught. It is 5 nanofarads. 5 nanofarads. That's the capacitor. So 5 times 10 to the minus 9, right? All right. Okay. So it's connected to the battery. So I'm going to ask you the first question. What's the charge on the capacitor? What can we say? Or what's the voltage across the capacitor first?
CE.
What's the voltage on the capacitor? Let's do the voltage.
160.
Huh?
160.
160.
Yeah, 160. It's
Yeah.
that of the battery. Yes. So 160. Volt. This plate will be positive, right? This plate will be negative.
Yeah.
Not that it matters, but just to be sure. 60 volts. Okay. So how do I get the charge on this capacitor? Good. Yeah, it is CV, right? We're referring to, by definition, capacitance is Q over V, so CV is Q. So let's multiply them. 160 times 5 is 800 nanocoulombs, right?
Mm-hmm.
So the 800 nanocoulombs. Let's figure out what the energy is. What's the energy stored in this capacitor? Okay. 1/2 CV squared, you said? Well, let's do that. But don't forget to make nano here, right? Times 10 to the minus 9. So when you multiply, you should get a small number because it's nanofarads. And I'm going to simply code the answer. 6.4 times 10 to the minus 5. 6.4 times 10 to the minus 5 joules. Okay. So far so good, right? We didn't do much yet. We're going to disconnect it now from the battery. And then I'm going to ask you certain questions. So we're going to disconnect. So here is your capacitor. So if you cut the wires, you just disconnect the capacitor. Does the charge change?
No.
No.
No, it stays the same. So you still have a charged capacitor. So the charge is still going to be this. I'm sorry, this, that's the charge. How about the capacitance? Does that change from 5 nanofarads? No, it's still the same capacitor. We didn't add a dielectric, we didn't change the area, we didn't change the distance, we didn't do it. So C naught is the same, Q is the same, so the potential difference across the capacitor is still the same, even though it's disconnected. That's why I said, even though an appliance may be not plugged, if a capacitor is there, it might be station charged. So here, again, everything that we said here is still here, right? We're disconnected. Next step. So we're going to fill it up with a dielectric. They say here, immerse it in water, pure water. Water. What's relevant is not its water, it's that kappa is the kappa. So here's the dielectric. And it's full of